to discuss transistor biasing circuit. In our syllabus, transistor biasing circuit, two circuits are needed to study. That is the fixed biasing circuit and voltage divider biasing. In this class, in this lecture, we will focus on fixed bias. Before going to the biasing technique, we can check what are the stability factors. Stability factor S is defined as the change of collector current with the leakage current. At that time, the base to emitter potential and the current gain beta should be kept constant. The stability factor S dash should be equal to rate of change of collector current with base to emitter potential. At the same time, IC leakage current and beta should be kept constant. And the stability factor S double dash should be is equal to change in collector current with the change in current gain, that is delta IC by delta beta. At the same time, the leakage current ICU and VB should be kept constant. These are the stability factors of transistor circuit. Stability for a common emitter configuration, collector current is given as collector current IC equal to beta IB plus leakage current ICEO. The leakage current ICEO is expressed as 1 plus beta times ICBO. When ICBO changes by delta ICBO, IB definitely changes by delta IB and IC changes by delta IC. So this equation becomes delta IC equal to beta times delta IB plus 1 plus beta times delta ICBO. Taking delta IC on the right hand side, we will get 1 equal to beta into delta IB by delta IC plus 1 plus beta into delta ICBO by delta IC. 1 minus beta into delta IB by delta IC equal to 1 plus beta times delta ICBO by delta IC. So by arranging the equation, we will get delta leakage current by collector current is equal to 1 minus beta times delta IB by delta IC divided by 1 plus beta. So we already know that the stability factor S equal to change of collector current with the leakage current. At the same time, VB and beta should be kept constant. So from equation 1, we will get stability factor S equal to delta IC by delta ICBO. From the above equation, this term can be replaced by the stability factor S. So the expression will becomes S equal to 1 plus beta divided by 1 minus beta delta IB by delta IC. The above equation is the standard equation for derivation of stability factors of other biasing circuit also. In our biasing circuit means we have to provide external DC source to the transistor to operate in the linear region. When the transistor is operated in the active region, we have to apply emitter base junction, that is forward biased, and collector base junction should be reverse biased. Here the transistor is NPN transistor. Emitter base junction, P terminal is connected to positive terminal and N terminal is connected to negative. So the emitter base junction is forward biased. Likewise, negative is connected to positive terminal of battery in the collector base junction. So the collector base junction is reverse biased. This is the basic biasing circuit. In order to use, we had to bias the transistor in the active region. So in normal scenario, we are not using two battery sources. Instead of, we are connecting In the common emitter configuration, we are biasing using normal scenario. We are biasing using two battery supply. That is NPN. Emitter base junction is forward biased, means positive terminal is connected to positive, and collector base junction is reverse biased, means negative terminal of the battery is connected to positive. This is the general biasing circuit we already studied in order to operate the transistor as in active region. In normal case, in electronic circuit, we do not bias the circuit using two battery sources. Instead, we are using a single power supply to bias the circuit. Instead of using two battery sources, we only provide a single power supply to bias the above circuit. We can redraw the circuit using single power supply. Transistor is placed as such, and in the collector resistance, we are connecting collector resistance. We are connecting a single battery, that is VCC, that is the positive terminal of the battery is connected to positive terminal of the battery is connected to the collector resistance. In the same scenario, in the base lead also, this is the normal biasing circuit we are applied. Instead of using two battery sources, we can replace this base resistance. RB is connected to positive terminal of the battery sources. Instead of using two power supplies, using single power supply, we can attain the same biasing network. This biasing circuit is called as, simple biasing circuit is called as fixed bias circuit. രണ്ട് ബാറ്ററി സപ്ലൈ യൂസ് ചെയ്തിട്ട് ബയസ് ചെയ്യുന്നത്, എമിറ്റർ ബേസ് ജംഗ്ഷൻ ഫോർവേഡ് ബയസും കളക്ടർ ബേസ് ജംഗ്ഷൻ റിവേഴ്സ് ബയസും ചെയ്യുന്നത് സെയിം അപ്ലിക്കേഷന് ഒരു ബാറ്ററി കൊണ്ട് ചെയ്ത് എടുക്കുന്ന ബയസിങ് സർക്യൂട്ടാണ് ഫിക്സഡ് ബയസ് സർക്യൂട്ട്. സർക്യൂട്ടിൻ്റെ അറേഞ്ച്മെൻറ്റ് ഇങ്ങനെ സെയിം കോൺഫിഗറേഷൻ തന്നെയാണ്, ഒന്ന് റീപ്ലേസ് ചെയ്ത് വരച്ചു എന്ന് മാത്രം. ഫിക്സഡ് ബയസ് സർക്യൂട്ട്. Fixed bias circuit using only a single battery supply. Biasing using a single power supply is so called as a fixed bias. A transistor is biased to fix the operating point, and it can be done by different method. One of the simplest method employed is a biasing using single power supply, that is fixed bias. Here the transistor is driven by VCC through the resistor RB. The resistor is suitably selected to ensure proper region of operation for the working. Here IB is the base current, IC is the collector current, RB is the base resistance, RC is the collector resistance, and VCC is the supply voltage. This is the general arrangement for a transistor to operate as an active region. So this circuit is just redrawn like this. In order to provide two separate power supply, that is VBB and VCC, we can use a single battery instead of two, as shown in figure. This simple biasing circuit is called as biasing using single power supply or fixed bias circuit. Instead of using two battery, we can replace with a single battery. That circuit is called fixed bias circuit. The base current is represented by IB, collector current is represented by IC, and emitter current is represented by IE. We can analyze the fixed bias circuit into two parts, input section and output section. In the case of input, that is the base to emitter lobe, this is the input section, base circuit. Apply KVL to the base circuit, what will get? VCC minus IBRB minus VBE equal to 0. From the above expression, we can get the value for IB. So, VCC minus VBE equal to IBRB. So, IB equal to VCC minus VBE divided by RB. Or we can the approximate VCC is very much greater than the VB. VB here is the base to emitter potential, that is the diode drop. For a silicon, the potential drop VB is approximately 0.7. We can approximate IB as VCC divided by RB. We can omit VBE since VCC is very much greater than VBE. The supply voltage VCC is of fixed value. Once the resistor RB is chosen, IB is also fixed, and hence this circuit is also called as fixed bias circuit. We can analyze the output loop, that is the output loop of the fixed bias circuit. This is the output loop. Apply KVL at the output loop, what will get? VCC minus ICRC minus VCE equal to 0. So VCE equal to VCC minus ICRC. From the above circuit, we can get the coordinate of the operating point. That is the coordinate of the operating point is the VCE and IC. Collector to output voltage is collector to emitter voltage, and output current is collector current IC. From the output equation, we can obtain the collector to emitter potential, that VCE, and from the input loop we can get the since stability factor S for a fixed bias circuit IB is approximately equal to VCC by RB. When IB changes by delta IB, VCC and VB are unaffected. Delta IB by delta IC is equal to 0 since IC is not present in the equation. Substituting this value in the above equation, that is equation number 5, that is S equal to 1 plus beta by 1 minus beta into delta IB by delta IC. Stability factor S we will get as 1 plus beta. We can also, we know the collector current expression as IC equal to beta IB plus beta plus 1 ICO. From the collector loop, we already find out the VC expression. So the collector current IC equal to VCC minus VCE by RC. IC equal to, here substitute for IB. IB, we already got that IB equal to VCC by RB. Substitute equation 2 in 5. We will get equation 2 in 3. IC equal to beta times IB, that is VCC to RB plus beta plus 1 ICO Differentiate equation 5 with respect to ICO leakage current. Stability factor S becomes beta plus 1. This is the stability factor for fixed bias circuit. Since the stability factor is beta, current gain of the transistor is very high, stability factor is very high. So, fixed bias circuit offer poor stability since S is very large.